you? Good. Doing well? Friday? Good? Okay, so a couple announcements. I finished grading for your first and second practice exam. By the end of today's session, all of the scores will be uploaded on the Blackboard. You can see it. But don't worry, because that's not going to be on your grade, right? This is going to be the most important thing, the sign-in sheet. So please don't forget to put your signature on the sign-in sheet. And there is a handout for today and next Friday's class, which will cover the engineering economics. Okay, so today we have Dr. Pontius to cover the first half of the engineering economics, and next week we have Dr. Ian from CSDS who will cover the remaining part. Okay, so please bring your material next week as well. All right, so here we have Dr. Pontius.
Engineering economics, for a number of years we didn't have a particular class in it. I think some of the departments have a class. In my experience, with a little bit of study, most students pick it up. Okay? It's not theoretically difficult. It just takes time and attention. So if you give it some attention, work through the problems, I don't think you'll find it that challenging, and it should be an easy, correct answer on your exam. Okay? It's not that hard. So I'm going to go through a series of slides I've put together over several years, talk about some principles, and then go through typical problems that you could be asked to solve. I have an example of each one, and some of them you might be familiar with, some might be new. Let's see if this will work here. Okay. Why do we do this? Why do we do engineering economics? What's wrong with just business economics? Okay? Or financial economics? Because they're not the same. In engineering, we want to know, well, is this project something we want to do? Right? From a financial standpoint. And if it's not, well, maybe we don't want to do it. If we don't know that going in, there could be any number of things that could happen once the project gets going, if it gets going at all. So if it's an undesirable project, it's never going to get started. It just gets put on the shelf, forget about it. So it has to have some benefit to it, and we just lost our screen there. Oh, that's okay. All right. Okay. It could be delayed. Things happen beyond our control, right? Economy and other kinds of things, funding, people working on projects, businesses, or in my case, I'm a civil engineer, municipalities, they make decisions. They can delay. Fire! I'll just yell. Okay, delayed start. Well, we could complete it, but if it's not sustainable, it's not economically sustainable, right? It's going to fail. Now, I know this might not be popular to say, but we know that from civil engineering, the ASCE, that there's a large infrastructure need in terms of funding to rehabilitate quite a bit of infrastructure. Well, why is that? Well, part of the reason might be because it wasn't really thought through well enough to begin with. Okay? So every project that's been built, well, maybe it doesn't need to be rebuilt. Maybe it should be replaced, right, for something else, some other solution found. Because it will fail. It's just a matter of time. It'll wear out in terms of civil infrastructure. Often, when things don't go right, projects tend to run out of money, perhaps towards the end when you're just about ready to complete them and open open shop, at least for structures and businesses, you might find yourself in a dispute. Usually it's between the engineer, contractor, and owner. But it could be, in fact, it could be within an industry or a business. You're selling a product, and when you think the product's going to do something that it really doesn't, isn't sustainable economically, and then when that happens, there's pressure on the business to find, well, who's responsible for that stupid decision, right? And maybe try to recover some of your loss, right? Or, in some cases, you'll go out of business. And this is a reality today, right? We see a lot of empty shops that used to have businesses in them. Just when I drive around, okay, so there are a lot of outcomes possible when I start a project, whether it's a civil project, whether it's a new toaster, right, or a new solar panel. It really doesn't matter. It could be any of these outcomes. So engineering economics then is used to compare options. So in any project I'm working on, I have one or more options I can consider. Maybe there's just a few of them, like in this case, I've got 3 options, 1, 2, and 3. I want to know, well, is any one of those, they're different. Sometimes their options are very different. Which one is more economically attractive to pursue? Well, that's the question we're trying to answer. Why do we do this? Well, we do this to avoid this, right? Money down the drain. That happens. Okay, that happens, but this is what we're trying to avoid. Wasting our money, going down an unsustainable path or a less desirable path on a project. That's true for any project. Now, in engineering economics, again, it's not financial economics. We're not trying to finance a project. And we're not trying to run the project like a business. We're trying to compare alternatives. So certain things we consider, other things we don't need to consider because they're the same regardless of what the alternatives are. And you'll see as I go through this, hopefully, a few of those. So we simplify the problem. We make some assumptions. The first one is something called the year-end convention. Now, during every day, money is flowing, right, in and out of any project. And if I'm doing an economic analysis, it'd be a little bit tough to try to account for that money flow on a day-to-day basis. So what we do is we assume that all expenses or benefits will come in at the end of the year. End of the year. So it's a year-end convention. So when you look at the cash flow diagrams I'm going to show you, well, you see it all being spent or the income at the end of the year. Even though we know it's not that way in the real world. No inflation. Unless you specifically want it, there are ways to account for it. But it complicates matters, and who knows what that's going to be in the future. If I'm just comparing alternatives, it probably is not going to affect the outcome of the comparison. So I don't have to consider that, really. Taxes in the same way, before tax. Now, there's sometimes when you'll want to do tax considerations, but they're rare, and I wouldn't expect anything like that in terms of your exams or even in practice. Effective interest rate is constant. We deal with interest rates, we have to make some assumptions, and we assume they don't change over the life of a project. So if our economic analysis is over 30 years at 2%, we assume it's 2% for 30 years. Well, how likely is that? I don't know. But again, we're comparing alternatives. We're not trying to predict the future, right? Non-quantifiable benefits. Non-quantifiable benefits and costs are disregarded. This is important to understand. When I do an engineering economic analysis, if I can't quantify it, right, I can't put it in terms of dollars, okay? I can't put it in terms of dollars, I can't consider it in my analysis. So I might do my analysis and get my three alternatives, and this one is the lowest cost, but we're going to do this one. We're not going to do that one because of the non-quantifiables. That might drive the decision. And that happens, that's okay. We assume the funds are available, not competition, and excess funds are at the interest rate that we assume. Okay, how do we express the results? Well, we're not looking for accuracy. In fact, we may not even need the accuracy I'm going to go over. 4 significant figures is sufficient unless the first digit is a 1, then 5 maximum. So let's look at some examples. $68.27. Well, we would just call it $68. In fact, I could probably call it $70 and end up with a similar result. For $75,121, well, we drop the 1 on the right, right? $75,120. So those are my 4 figures. If I've got the first one as a 1, like here, 1,135,225.23, right? Well, you drop the last four numbers. So 1,135,200. You could probably skip the 200 as well in reality, but this is typically the convention that we use for reporting. Okay, so let's walk through some principles. That's the kind of why we do this. And I have to emphasize this. You may not be doing these kinds of calculations or doing profit loss statements or economics, but I guarantee you someone, whoever you're working for, is doing this. And whatever project you're working on, if it's not going to satisfy some conditions in terms of economics, like benefits greater than the costs, right? You don't have a project. So the pressure is on, right? The engineering, as well as everybody else involved, whether it's marketing or manufacturing, okay? So you've got to do what? Top quality job, right? Creative, with no money, right? That's the ideal. Low money or no money. And they want it yesterday, too, okay? So here we go. Right? Engineering, economics considers the time value of money. That's one of the things that's important. It sometimes drives the decision. What do I mean by time value of money? Well, if I'm going to borrow money, whoever I borrow the money from, I borrow $1 million from the third row here, and you could loan me $1 million, that's great. You probably want something in return, right? I mean, you're not just going to give me free money to use without having some benefit come back to you. And that's the interest that you're going to charge me. So interest is charged on the money from the lenders. It could be simple interest, which represents the interest on the loan amount only. There's no time factor involved. It's a one-time charge, right, on the principal. Compound interest, though, well, that's a little bit more. Interest is charged each interest period, whatever it is. Now, in our analysis, it could be a year, could be a month, could be a week, whatever the interval is between the time I charge my interest. Okay, that's my interest in period. And both the principal and interest accrue interest. The interest adds up. So after year 1, I make my payment and I pay interest. After year 2, I'm going to make my payment, pay the interest on the original loan, as well as any interest that's been accumulating, right, from that over and above that amount that I had to pay last time. All right. Let's go through an example. $15,000 borrowed at 2% interest over 60 months by a car. Annual compounding Okay? In economics, we use some standard notation, and it's easy. It's not hard. And it's not this. This is what I cooked up, right? My total paid for the compounding interest, okay? But here's where it gets standardized. It's the amount times a factor. A factor. This particular notation here deals with the type of factor I'm going to look up, okay? This is the interest rate that's being assumed, 2%, and this is the time period, 5 years. 5 years, 2%, and then whatever this represents, and you'll see shortly what that is. So I look up that factor in a book where I can use an equation to calculate it. It's 1.104, I multiply these two together, and over the life of that loan, I'm going to actually pay $16,561, not $15,000, because the interest has been compounded. Okay, well, what does it look like with simple interest? Just to show you the difference. If it's just a simple interest loan, actually people still do this. I bought a car on a simple interest loan from a dealer, believe it or not. It was hard for me to believe, but that's the case. It would be 2% on the original loan amount, and that's all. So 2% of 15,000 would be added up, $15,300. So which one would you want to pay, right? So the difference is $1,261. So by compounding the interest over that time period, well, the payment's more, right? You'd expect that to be the case. Project costs and benefits occur at various times, and there's some standard notation, right? Once you learn this, again, it's not hard. P, well, P is present, like today, present. F, what do you think F is, right? Future. It's the future. A would be annual, every year, annual. And G would be gradient, generally increasing the same amount each year, right? Linear increase, typically. Or it could be an exponential increase. We can handle either one. And so with that notation then, every project has a cash flow. What the project is, you're going to have expenses. Hopefully you're going to have some income to cover the expenses. The expenses could be materials, it could be labor, overhead, whatever the expenses are, you'll have expenses. You're going to have some income to pay for that. Right? And in that exchange over the life of the project, there'll be a flow of cash in and out of the project. And that flow of cash can look different depending on the project. So very typical in a project, when it starts, you're going to have an initial capital cost right up front. And we would designate that cost with P, with an arrow pointing up. So this is called a cash flow diagram. Okay? Cash flow diagram. Single payment. So I have a very simple project, and in fact, in this case, when it's going up, actually, that's not a bad thing. All right, let's keep going. Here's, what do you think? Annual, or in economics speak, okay, it's uniform series. Uniform series, the same amount each year for the entire life. Same amount each year. So, uniform series, when you see a cash flow look like this, well, then there's a certain way you handle it. Right? We'll go over that. It could be a gradient that's increasing linearly, gradient series, or maybe it's an exponential gradient in series. Of course, you can have other ones and develop a math for it, but these are the typical ones that you face in a project. And on exams, you know, generally you're looking at these first two. Maybe they give you a problem with the gradient, but generally it's going to involve the first two. That's a practical matter. So let's do an example cash flow problem. The first step you want to do in solving an economic problem when you're given like this, and this is the likely one that could be on a test or something like that. I taken from I used to teach this in Colorado. Okay, so you'll see real problems here. The mechanical device costs $20,000 when purchased. Maintenance will cost $1,000 each year. The device will generate revenues of $5,000 each year for 5 years, after which the salvage value is expected to be $7,000. Draw and simplify the cash flow diagram. So that's the problem. Draw and simplify the cash flow diagram. Now this wouldn't be an example test problem because they're going to have options for you, A, B, C, or D, and they'll probably show you some cash flow diagrams and you have to pick the right one, right? That's more likely an FE style problem. But in this case, let's try. Where would we start? Well, I have a cost of $20,000, so I'm going to start at year 0. I got to shell out $20,000. That's going to be a downward pointing arrow, $20,000. So what I pay out, arrow goes down. What comes into me, arrow goes up. Right? $1,000 each year. Well, I'm going to have a series of arrows after every year, 20 down. And revenues of $5,000 each year. That's good. I want that coming in. 5,000's coming in. The arrow's pointing up each year. And my expected salvage value at the end of the project, I'm going to sell my used car or whatever it is, right, machine, and get $7,000 for it. So this is what I would draw. This would be plot all of the cash flows, all of the flows on one diagram. Even if it's a simple one like this, you got $20,000 cost. Okay, that's at 0. We don't put that at the end of the first year. That's 0. That's my initial outlay. Then at the end of the first year, I'm going to have $1,000 maintenance, right, going all the way up. $5,000 a year of income at the end. I'll have my $5,000 per year of income and $7,000 of salvage value because then I'm going to sell it. Okay. So I draw all the cash flows in and out on a line diagram like that. Right? Standard, I call it a cash flow diagram, and then I can simplify it. Right? I simplify it by combining the values. So I just subtracted, $1,000 from 5 and a $4,000 net increase each year, right? And then at the end, I'm going to have $11,000 income, $5,000 from my manufacturing process, and $7,000 from the sale of my equipment. Okay? So cash flow diagram. Why is that important? The cash flow diagram is important because money may have equivalent value at different times. And so let's go through a little bit of an example to try to illustrate that. $100 placed in the bank at 5% interest. That's kind of wishful thinking today, right? You get 5%. Okay. Well, let me give you 3 options. Right? And you tell me which one you pick. I could give you $100 today. I can give you $105 in a year, or I can give you $110.25 in 2 years. Which would you want? Okay. When you consider the time and the interest, they are equivalent values. Now that doesn't mean that they're all equally desirable, right? $100 today beats them all as far as I'm concerned, right? Because I got it right here. And this is important now, right? I can make a promise to give you $105 in a year, but, maybe I'm not going to keep it. Right? Well, that happens. So, in the analysis that we do, these are equivalent. And that's important because we're going to have outlays in the future, and I have to be able to draw them back to some kind of equal comparison. I'll show you how to do that. We do that by using factors. Now, you don't have to. This shouldn't cause brain damage. I hope not. But these are all the factors. In fact, this is the table right out of the FD manual. Okay? Your FD reference manual, you want to read that carefully. Okay? There are 2 or 3 pages dealing with economics. You want to see what they're giving you. What they're giving you will be clues to the kind of problems they're going to ask you. So this is the table, and these are the factors.